So chemical potential. Can we use enthalpy to measure chemical potential? Anybody remember what enthalpy is? It's related to that, yeah. It's heat exchange at constant pressure. So in 1A we learned about, I just taught this like 2 weeks ago, so I'm like, okay, I remember this stuff right now. We learned about internal energy, which is E, and how, we don't really have a zero that we can measure from. So like in changes of elevation, we have chosen to use sea level as zero. And we reference everything to that. And so with energy, we do that as well. Most of the time, we're looking at a difference. And so exactly where zero is doesn't matter. But there's internal energy. And internal energy is the sum of all the forms of energy that a substance possesses. So enthalpy, if you're doing a process at constant pressure, is equal to the heat exchanged. So enthalpy predicts that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. Are there spontaneous endothermic reactions? There are. What about those instant cold packs? Right? You break it open, chemical reaction occurs that's endothermic. It's pulling energy in, and the thing gets cold, makes your hands cold, right? That's an endothermic process, but it's spontaneous. So enthalpy is not going to tell us. A lot of exothermic processes are spontaneous, but not all of them. So this is not the answer. So here are a couple of things that spontaneous processes that involve an increase in enthalpy, which you would expect to be non-spontaneous. So the melting of ice above 0 degrees Celsius. When you melt ice, what happens? It takes energy in, right? It's an endothermic process. The evaporation of liquid water, is that exothermic or endothermic? It's endothermic. The dissolution of sodium chloride in water, also an endothermic process. But they're all spontaneous. The thing that all of these things have in common that's important for spontaneity is that in each process, disorder or randomness is increasing. So entropy is the word that we use in the concept that's the criteria for spontaneity in chemical systems. So very informally, we can think of entropy as disorder or randomness. And there are a lot of processes just in everyday life where you observe that the spontaneous process is making things messier, right? If you take a deck of playing cards, right, and throw them in the air, are they going to land in a neat stack all in the same order? No, they're going to be messy all over the place. You think about a tree that grows leaves, right? Those leaves are ordered, right? Each kind of plant has a different pattern for how its leaves are placed on the twigs, etc. What happens in the fall? The leaves fall. Do they fall into neat piles? No, they go all over the place. It gets messier, right? So when this, I believe, is at Yellowstone, here there's water that's evaporating. And as the water evaporates and goes into the gas state, there's an increase in entropy, an increase in disorder. When sodium chloride dissolves, here the sodium and chloride ions are all very neatly arranged, very precisely, three-dimensional, regular order. When they dissolve, they become more random and they just kind of go all over the place, right? Wrong way. So entropy has the symbol capital S. Don't ask me why. I don't know. There's no S in entropy. E was taken by internal energy, which, in retrospect, maybe should have been an I, but whatever. So S is entropy. So this is something that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. That's a little bit hard to understand. We'll have some pictures coming up. So entropy is a constant times the natural log of a capital W. So K is the Boltzmann's constant. W is the number of energetically equivalent ways that the components can be arranged. Now, we very rarely calculate entropy this way. Usually we're looking at change in entropy. But the units of entropy are joules per Kelvin, because those are the units of the Boltzmann's constant. So, imagine a fixed amount of an ideal gas. We've got constant pressure, constant volume, constant temperature. The state of the system is defined by the pressure, the volume, and the temperature. The energy of the system is constant. But exactly where the energy is within that sample is not constant. At any one instant, a particle over on this side of the container might have high kinetic energy, and then it might collide with something else, resulting in it having low kinetic energy. So the particles can change in their kinetic energy. The temperature is a measure of the average kinetic energy, right? But not all the particles have the same energy, and they don't retain the same energy. They can change their energy. So macrostate is the overall big picture. Microstate is like a snapshot, the exact internal energy distribution at a given instant. So one macrostate can have lots of different microstates. The microstate changes as the energy is redistributed among the particles, but overall the macrostate remains the same. So we can think of W as the number of possible microstates that can occur. Okay, now this might be a little easier to understand. So here we have two systems, system A and system B. Each system has two particles in it, and the total energy is 4 joules. Okay. System A has one energy level, and both of the particles are in that one energy level. So there is only one microstate. There's no other arrangement. System B has 2 different energy levels. And so we have 2 possible microstates. We can have the red with an energy of 3 and the blue with an energy of 1. Or the blue could have 3 joules of energy and the red could have 1 joule of energy. Overall, the macrostate is the same. There's 2 particles, 4 joules of energy total. But this one has 2 ways that the energy can be distributed. This only has 1 way. The entropy of system B is larger. There's more possible ways for it to be arranged and still have the same energy. Any questions?
Why does it for system A say that the E is 2 joules?
So the energy level here is 2 joules, meaning that particle in this level has 2 joules of energy. So they each have 2 joules, and so a total of 4. Here you have one that has 1 and one that has 3, and the total is still 4. Good question.
Because I was like, am I subtracting something?
Yeah, what's going on there? Any other questions? So the entropy of a given macrostate increases with the number of energetically equivalent ways to arrange the components. The state with the highest entropy also has the greatest dispersal of energy. So going back to this system, all the energy in system A is in this one level. In system B, there are 2 levels. The energy is dispersed between the 2 levels. So a state in which a given amount of energy is more highly dispersed or more highly randomized has more entropy than a state in which the same energy is more highly concentrated. So what we'll see is that energy has a tendency to spread out. When energy spreads, entropy increases. So the second law of thermodynamics is that for any spontaneous process, the entropy of the universe increases. So in deciding what processes are spontaneous or not, the thing we're looking at is the change in entropy for the universe. So you can have a spontaneous process where the entropy of the system decreases, but there has to be an accompanying increase in entropy for the rest of the universe so that overall it's greater than 0. So entropy is a state function. The value depends only on the state of the system, not how you got to the system. How you got to that state. We talked about state systems in Chem 1A, state functions. I maybe should have brought my brain today. And the illustration they give there is people climbing a mountain. And there's 2 different paths. And this one was like 5 miles long, and this one's like 1 mile long. The change in elevation is the same, regardless of how you get from the bottom to the top. But this person travels 1 mile, and this person travels 5 miles. You could also have my preferred method is I'd be over here, and I'd get in a helicopter, right? And a helicopter would come up, and we'd fly over there, and then they'd gently put me down on top of the mountain, right? Change in elevation is the same, right? How you got there's not.
So this is in case we're applying to like a chemical level, introducing catalyst. It's not going to change the state of entropy or the state of energy that's used.
Yeah, I don't think a catalyst affects the entropy at all. It'll just affect how fast it gets to where it's going. Yeah. So there's kinetics and there's thermodynamics. And kinetics is how fast you get there, and thermodynamics is where are you getting, right? In an equilibrium, where does the equilibrium lie? Doesn't matter how fast it gets there, that's kinetics. So a chemical system will proceed in a direction that increases the entropy of the universe. So here we're looking at an ideal gas. We've got 4 particles here in this container, and on this side is a perfect vacuum. So when we open this, the gas is going to expand into the other side of the container, right? The pressure at which it's expanding is 0, so the work is also 0. It's another thing from Chem 1A. Work is equal to negative pressure times the change in volume. That's pressure volume work. If the volume changes but there's no pressure for it to expand against, no work is done. So when this expands, no work is done and the total energy doesn't change. But the entropy does. Because now we have some different possibilities. So when we open this stopcock, we could have state A occurring, where all 4 particles just stay over there. We could have a state where the 4 particles go to the other side. We could have a state where we have 2 on this side and 2 on that side. So those are different states. How many microstates are possible for each macrostate? So each of these is a macrostate. How many possibilities, arrangements of these particles are there for state A? 1. All 4 particles are over here. In this one, all 4 particles are on the other side. So in this one, we could name these guys, or, we'll call this guy A and B, and C and D, or, Steve and Harry and Sally or something. So if A and C switched places, the macrostate is the same, right? If B and D switched places, the macrostate is the same, right? So how many possibilities do we have there?
4.
So we've got A, B, C, and D. We've got C, B, A, and D. We've got A, C, D, and E.
You forgot CD on one side. DC on the left.
Yeah. So which of these macrostates has higher entropy? State C. Just, from knowledge of chemistry and general knowledge, which of these state is actually going to happen? State C, right? The gas will expand and fill the container uniformly. It's not just going to stay over here. Does that make sense? So here they're numbering them, right? So here we've got 1, 2, 3, 4 on this side, 1, 2, 3, 4 on that side. Those two states only have one microstate. But state C has 6 different microstates. So the probability of finding the atoms in macrostate C is 6 times greater than in A or B. The entropy is larger. So if you go from 4 atoms to 20 atoms, then you have 184,756 microstates for state C. State C being an equal number of atoms on each side. But for A and B, where all the atoms are on one side or on the other side, there's still only one microstate. So the change in going from state A, where everything's on one side, to state C, where you have equal numbers on both sides, the change in entropy is positive, and that is then predicted to be a spontaneous process. So as with all kinds of other things, delta means final minus initial. The final entropy minus the initial entropy. Another way to think about this, when those atoms in state A or B are all confined to one side, to one of the flasks, their energy is also confined to one side or the other. When the atoms are evenly distributed, the energy is evenly distributed, right? It's dispersed, it's spread out. So the second law of thermodynamics explains things that the first law of thermodynamics cannot explain. So here we have a beaker of ice water. The heat is going to travel from the water to the ice and not the other way around. The first law of thermodynamics does not prohibit the ice from getting colder and the water from getting warmer. That could happen. Energy can still be conserved, right? That's the first law. Energy is conserved. But according to the second law, energy will be dispersed and not concentrated. So the water has more energy than the ice does. And so a positive change in entropy will say, well, the heat is going to go from the warmer substance to the colder substance until the heat is distributed evenly, is more dispersed. So when substances change state, solid to liquid or liquid to gas, their entropy is going to increase. We can say that the gas state is more disorderly than the liquid state, right? The energy here also is more spread out than it is here. The liquid state is more disorderly than the solid state. But the official thing is there's more energetically equivalent ways of arranging the particles in a gas state than in a liquid state. More ways in a liquid than in a solid. So if we look at solid ice, the water molecules in solid ice are not moving relative to each other, right? It's kind of like you guys right now. Everybody's in the same position relative to everybody else. But that doesn't mean you're absolutely still, right? Everyone appears to be at least breathing, right? So there's energy, there's motion. But the water molecules are limited to vibration, to wiggling. They can only wiggle, right? You guys can squirm around in your seats, but you can't run around the room and still be in the solid state. But a gas has more places to put its energy. It can have translational energy. It can be moving across. It could vibrate. It could also rotate. Right? So it has a lot of different places it can put its energy. So it has more microstates. You could think of each of these types of kinetic motion as being a different level that something could be in, and so that increases the number of microstates. So entropy increases, delta S is greater than 0 for each of the following. Phase transition from solid to liquid, from solid to gas, or from liquid to gas. If we have a chemical reaction where we increase the moles of gas that are present during a chemical reaction, that will also have a positive delta S. Because you have created more gas than you had before. You know, the number of atoms and stuff is the same. Okay, predict the sign of delta S for each process. So, water going from the gas state to the liquid state. Negative. Right? So delta S is less than 0. How about solid carbon dioxide subliming? That's going to be positive. That's going to be an increase in entropy. How about this one? 2NO2 going to 2N2 plus O2. That will also be positive because we're going to larger number of moles of gas. Any questions? I am just dying up here. So when we have a change in state, in physical state, there's also going to be an exchange of heat between the system and the surroundings. Entropy is related to the distribution of energy among the particles that compose matter. So if we have a change in entropy where the system exchanges heat with its surroundings, I got lost in that sentence. We can define the change in entropy when the system exchanges heat. So here's the heat being exchanged with its surroundings at constant temperature. This Q, though, is the heat exchanged in a reversible process. And the temperature is measured in kelvins, as is often the case. I guess we don't define reversible process yet. That's coming. So entropy then is a measure of energy dispersal per unit of temperature. Hence the units, joules, energy, divided by Kelvin. So if something melts, it absorbs energy from its surroundings. Right? The energy becomes dispersed into the system, and the entropy of the system increases. Okay, so what do we mean by a reversible process? A reversible process is one that reverses direction upon an infinitesimally small change in some property. So ice melting in the surroundings at 0 degrees Celsius is reversible. Because if you take away just a teeny tiny piece of energy, of heat, that will reverse it and cause it to start freezing again. Right? Ice melting on the countertop or, in the sink, that's spontaneous, but it's not reversible. Because if you remove a little bit of heat from that, it's not going to start freezing. You're going to have to remove a lot of heat from it, get it to 0 or below before it's going to start freezing again, right? So reversible processes are in a state of equilibrium, and they can just very easily be shifted. They are highly idealized. So it's this kind of this thing we compare stuff to, but it's really not very common. Okay. Calculate the change in entropy that occurs in the system when 10 grams of acetone vaporizes from a liquid to a gas at its normal boiling point of 56.1 degrees Celsius. And we're given the heat of vaporization. Well, we only have one equation for delta S, and that's this one right here. This is the heat exchanged in a reversible process divided by the temperature in kelvins. So here, something vaporizing at its boiling point, is that a reversible process? Yeah, just like ice melting at its melting point is a reversible process. So the change in entropy is going to be Q divided by the temperature. Q in joules. So how do we figure out the amount of heat needed to do that? Yeah, we need to change acetone from grams into moles. Pish posh. H6O. So we're going to convert that to moles. Whoops. 58.078. And then what do? Yeah, we're going to use the heat of vaporization. So we want moles to cancel out, and we're going to get kilojoules. There's 29.1 kilojoules for every 1 mole of acetone. But the units of entropy are joules per Kelvin, so we need to convert this to joules. Fifty 10.5 joules. And then what do we need to do to the temperature? We need to convert that to Kelvin. So this is 50 10.5 joules. Now, your book is kind of sloppy when it converts to Kelvin. Sometimes it uses 273, and sometimes it uses 273.15. So here, because the temperature is given to the nearest decimal place, I think we should use the 273.15 instead of the 273. .25 Kelvin. So 50 10.5 divided by 329.25. Uh, 15.2 joules per Kelvin is the change in entropy. Any questions? Oh, look at that.